Hey guys, welcome back for another chemistry lesson. Today we're going to talk about energy in chemistry. So, a familiar thing that you have probably all had experience with is chemical hand warmers. And most hand warmers use the oxidation of iron as the reaction to provide that heat. And this is the chemical reaction that occurs here. It is an exothermic reaction. And the amount that your hand temperature rises totally depends on the size of the hand warmer and the size of your glove, as well as, how cold it is outside, etc. But mainly, this is determined by the amount of heat that is released by the reaction. So, even though chemistry is specifically the study of matter, energy affects that. Right? So, energy is the capacity to do work. Work is a force acting across a distance. That's a very physics definition, but that's what it is. All right? So heat is the flow of energy that is caused by a difference in temperature. And we can exchange energy in between objects through contact between those objects. So for example, through collisions, right? We have recently talked about gases, so collisions between gas particles is how we transfer energy, right? So we have a couple of types of energy that are important. First, we have kinetic energy, which is the energy of motion or energy that is being transferred. A specific type of kinetic energy is thermal energy. So it's number one, this is the definition of temperature, right? But it's specifically the motion of the particles themselves. All right? And so that's one classification of energy. The other one is potential energy, which is the energy that is stored in an object. In physics, you see this a lot as gravitational potential energy, which is just, I hold a thing up here and then I drop it and it falls, right? That stored energy that allows it to then fall and move is the potential energy. Now, in chemistry, we see it as chemical energy. So this is the potential energy that is stored as a result of the structure of the atoms, how the atoms are arranged relative to one another, how molecules are arranged relative to one another, etc. So that is chemical energy, and that's how we see it in chemistry. Now, the law of conservation of energy states that we can't create or destroy energy. So when energy is transferred between objects, converted from one form to another, or whatever, the total amount of energy does not change. We just have to think differently about how we think about that energy. For example, conservation is shown here between a system and the surroundings, right? So I have 1, 2, 3 energy between my system and my surroundings. Then I'm going to transfer energy, and now I have 1, 2, 3 energy after the transfer. So the system had more before, the surroundings have more after. Regardless, I still have 3 energy. It's just a question of where is it, what type of energy is it, etc. So I just used a couple of terms that I need to clarify so that we all are on the same page here. We define our system as the material or the process that we are studying that the energy is changing within. And then the surroundings is quite literally everything else. So what we do is we study the exchange between that system and its surroundings. All right, just to sort of clarify a few things here. Energy, we have some specific units that we use to talk about them. So kinetic energy is directly related to the mass and the speed at which the thing is moving, whatever it is. And so when we measure mass in kilograms and velocity in meters per second, we get this really ridiculous looking unit, which is equal to what we call a joule. This is the amount of energy needed to move a 1 kilogram mass at a speed of 1 meter per second. All right, you may have also heard of watts and watt hours and things like that. That's also related to energy. All right, so a joule is the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not the same calorie that you see on your food labels. Those are actually kilocalories, so related because kilo, got 1,000 of them, but not the same word. So keep that in your head, right? And so here, just for some energy conversion factors, for my class, we use joules. I don't even really look at calories, but you need to be aware of them, right? And so we've got calories, joules, and then kilowatt hours. So joules are over time, right? So yeah, that's how we've got our various units of energy. Just to give a little bit of perspective to those, to raise 1 gram of water by 1 degree Celsius, so that's 1 milliliter of water by 1 degree Celsius, it takes a little over 4 joules, but that's 1 calorie, which is 1/1000th of a food calorie. And it's 1.16 times 10 to the negative 6 kilowatt hours. This is the number that your electric company looks at, right? To light a 100 watt light bulb for 1 hour, it's 0.1 kilowatt hours. So 100 watts is 0.1 of a kilowatt. That is the same as 86 food calories, or 3.6 times 10 to the 5th joules. The amount that we use in running a mile approximately, with whatever mass and athleticism they considered in this, it's almost the same. It's barely any more than for that light bulb for an hour. And then the average U.S. citizen in one day uses about 250 kilowatt hours of energy, which is 2.2 times 10 to the 5th food calories, 9 times 10 to the 8th joules.